This is Mr. Morris here, and this is the Sandwich Theorem. So we're doing 2.1 Day 3 Precalc AB notes, and I hope you brought your appetite because this is definitely the Sandwich Theorem or the Squeeze Theorem. So what we have here is if g of x is less than or equal to f of x, so if g of x is less than or equal to f of x is less than or equal to h of x for all x not equal to c in some interval about c, and the limit of g of x as x approaches c equals the limit of h of x as x approaches c equals L, which is just some y value, right? Keep in mind when you're evaluating limits, you are finding a y value the function approaches as x approaches c. If that is true, then the limit of f of x as x approaches c will equal that same y value, L. All right, so this example says, show that the limit as x approaches 0 of x squared times the sine of 1 over x equals 0. All right, this problem, we're telling you the limit is 0, and we just have to prove that. All right, so we know the answer before we start. We very well may ask this question a little differently and just say evaluate using the Sandwich Theorem, which you will not know the answer to begin with is 0. So the first thing you always do when you're evaluating a limit is plug in the value you're approaching. So in this case, it's 0. So 0 squared is 0, but the issue becomes when I try to divide 1 by 0, that's undefined. So I can't take the sign of that. So I can't just substitute in my value. So that's where the Sandwich Theorem comes in. So the Sandwich Theorem relies on inequality. I have f of x here, I have f of x here, and it turns out to evaluate this then, this is f of x. All right, and so what I need to do is establish an inequality. All right, when I establish an inequality here, I'm going to start out with the sine of simply x, and then I'll progress to the sine of 1 over x and then get x squared in there as well. All right, so what I know for sure is that the sine of x exists between -1 and 1. That is simply the range of the sine of x. And so we know that from trig graphs when we first learned those, or the unit circle. So that is absolutely a true statement. Now the key to this is get an inequality with f of x in the middle, right? And then I need a g of x, which is up here, and an h of x on both sides, all right? Well, I need a sine of 1 over x. So this next step is an intuitive step, which I'm going to write and then explain more about it. If the sine of x exists between -1 and 1, I also know for sure that the sine of 1 over x also exists between -1 and 1. All right, the reason why I know that is because the sine of x in red here is really saying the sine of any angle, because remember the sine of x has a domain of all reals. So the sine of any angle, all right, decimal angles, radians, degrees, any angle will be between -1 and 1. All right, well, the sine of 1 over an angle will just be another angle. So that has to equal, or excuse me, it has to exist between -1 and 1. All right, now as long as x isn't 0, which is what our issue was that we're trying to avoid in the first place. Right, so that should show, or at least explain, that the sine of 1 over x has to also exist between -1 and 1, because it actually is the sine of just some other angle. All right, this next step though, so if we think about this, I'm in pretty good shape. I have the sine of 1 over x between two values, all right, -1 and 1. I need an x squared in this inequality. Well, algebraically, and so this next move is an algebraic manipulation in which I want to get an x squared inside here. Well, to do that, I could multiply it by an x squared. But with all inequalities, then I have to multiply -1 by x squared and 1 by x squared. As long as I do that, I maintain this to be a true inequality. So I'm going to write this over to the side, and I'm going to multiply by x squared. So if I multiply by x squared, I'm going to multiply -1 by x squared. I get -x squared. I'm going to multiply the sine of 1 over x by x squared. And I get x squared times the sine of 1 over x. And then I multiply 1 by x squared, and I also get x squared. So this step in green is the first step I used algebra to manipulate the inequality. In the blue step, I did not use algebra. I didn't divide or multiply through by 1 over x or anything like that. I simply made an intuitive step or knowledge that both of those are true. All right, so actually, if you look at what's going on here now, and let me go back to this red, that's f of x. And so I have inside this limit, now inside this inequality, and I have managed to squeeze that function between negative x squared and x squared. All right, and that's all in good, or all well and good, as long as I can find the limit of g of x and the limit of h of x. And so in this case then, back to this inequality over here, g of x and h of x, well, negative x squared is my g of x, and x squared is my h of x. All right, and so let's see how this plays out in this statement that I'm going to make. So this is going to work as long as the limit of negative x squared as x approaches 0 and the limit of x squared as x approaches 0 both give me the same value, and they do. So since the limit as x approaches 0 of negative x squared. All right, so this is a limit and this is a polynomial now. So as you've learned before, polynomials are fairly easy to evaluate the limit. I simply plug the 0 into my function. So 0 squared is 0 times negative is still 0. So that's a fairly easy limit. All right, remember to always plug in your value. If you get an answer out that's not undefined, then that is your limit. And also, so over here I took the limit of g of x, which is negative x squared. So here I want to take the limit of h of x, which is x squared. So the limit of x squared as x approaches 0, well, again, this is a polynomial. If I plug 0 into x squared, 0 squared is 0. That is also 0. Well, way up here, if the limit of g of x equals the limit of h of x, in this case as h approaches 0, not h approaches 0, my apologies, as x approaches 0, is L. Well, if that is true, then the limit of f of x, which is what we're looking for in our original limit, equals that same L. All right, so since those two things are true, the sandwich theorem then tells me that the limit of x squared times the sine of 1 over x as x approaches 0, don't forget proper notation there, has to also be 0. So all of this has to be written for this proof or for this example. Other than this, you don't have to write that you multiplied by x squared. All right, so let's kind of backtrack here and recap what happened. We started out with the simple statement of the domain of the trig function that's in here. Now, sometimes this could be a sine or a cosine. There's variations of this problem, but they don't get all that different. All right, you have to start out here. Don't start out at the blue step. From the red step to the blue step, that is an intuitive step saying that if the sine of x exists between negative 1 and 1, so does the sine of 1 over x. Has to. Because 1 over x is just simply some other angle, and I can take the sine of that. All right, from here to here, from the blue to the green, that step is an algebraic step, which I wrote over here and underlined, is multiplied by x squared. All right, that's how I got the x squared in there. All right, and then the key after that is take the limit of this function and the limit of this function, And if those have the same values, you've managed to squeeze this function f of x, which we were looking for, in between those values, and they have to be converging really to the same value. All right, and you have to write all this up. All right, especially this last statement where I wrote since the limit as x approaches 0 of negative x squared equals 0, and the limit of x squared as x approaches equals 0, then the limit of x squared times the sine of 1 over x as x approaches 0 also equals 0. All right, one common mistake is to start writing limits from the left and the right. I know this function negative x squared happens to be on the left of the inequality, and this is on the right of the inequality. All right, but this has nothing to do with one-sided limits. These are all two-sided limits. I didn't approach from the left or the right, so my notation here is very important. All right, so that concludes the sandwich theorem. What I want to do real quick is to see if we could graph something like f of x equals the absolute value of x. Sorry about that. See if we can graph the absolute value of x over x. I think we can do it. All right. So in this graph, I'm going to start out by realizing right away I can't plug 0 in. All right. If I plug 0 in, I get it undefined. All right. So something's going on at 0. Now keep in mind, this is not really defined as a rational function because that would have to be a polynomial over a polynomial, and absolute values are not polynomials. All right. So let's start plugging in positive numbers. If I plug in 1, the absolute value of 1 is 1, and that'll be over 1, which is still 1. The absolute value of 2 over 2 is going to also give you 1. And so you can quickly see that the top always stays positive, all right, and the bottom will be positive, and you're simply dividing a number by itself. So this graph will look like this. I'll have at 1, I'm going to have a hole where x is 0, and it's going to have a horizontal line onto infinity when x is greater than 0 at y equals 1. All right, so then what happens when I start plugging in negative values? Well, the numerator will stay positive because the absolute value of negative will become a positive. The bottom, however, will always stay negative. And so if I have 1 over negative 1, that's negative 1. 2 over negative 2, that's negative 2. Excuse me, that's not correct. 2 over negative 2 is actually negative 1. 3 over negative 3 will be negative 1. So you'll always get a positive of the same value divided by a negative of the same value, resulting in negative 1. So this is negative 1. You'll have a hole here, and it'll graph, whoops, something like that. It'll go to negative infinity at x, but it'll always have a horizontal line at y equals negative 1. All right, so in this then, we could ask you to find the limit as x approaches 0. We could ask you to find the limit as x approaches 0 from the left, from the right. And you, from now on, need to know the graph of the absolute value of x over x, along with all of your other parent functions. You have got to be able to recognize a graph right away. So if we ask you what x squared looks like, or the absolute value of x, or x cubed, or the square root of x, or 1 over x, if we're going to require you to find the limits of these graphs, and after they're transformed, meaning with h and k, where their vertices or their graphs are moved around horizontally, vertically, stretched, compressed, you have to be able to do all that without a calculator to find limits graphically. All right, so that concludes our lesson. If the sandwich theorem made you hungry, go grab a snack. Have a good day.